Thank you so much for this opportunity to visit and what we have been doing for the last maybe 2 decades maybe. So a couple of things are like this data is very essential to do computation for topological string integrality, conjecture checks and so on. So I think at this level we need to get an explicit polynomial form of the invariance for all knots is something which is still a challenging question. What is the current status? What is happening is what I wanted to share with you. And even this terminology, I always knew it as knots and links, but this separation as arborescent or non-arborescent is apparently not new. It was known to convey is what Joseph was telling me in Aspen, and he showed a paper which was I think 1920s or something, where they have a very clear understanding drawing the knots as some kind of a tree. Okay, so there is a distinction. Arborescent is different from non-arborescent. There are some technology to work out the polynomial form for these arborescent. There are different technology to work out for non-arborescent. And there are some overlapping set where the technology is useful one for the other and so on. So I thought let me just give a flavor of how to do this. Okay, so these are my collaborators. The first line, Satoshi and Zodin, my students, former students, now the present students, Vivek and Shashwati. Vivek has just submitted his thesis. And I also have a Russian, Indo-Russian project where I have a team of Russian collaborators from whom we essentially learned how to handle non-arborescent knot invariants. Yeah, and we keep updating in a dedicated website all our results. Am I audible? Okay, so let me give you a brief introduction and then plunge into showing on the blackboard maybe how to do the computation for arborescent knots. And then there are several other methods of doing non-arborescent knots like highest weight, eigenvalue hypothesis. And then we mix and match both the combinations, which I call it as a hybrid approach, where we could use the tools to evaluate some knots which are non-arborescent but can be computed using a hybrid approach. And some of the open problems, since it's a workshop, I have been working on a couple of things. There are things which I don't know how to do, so maybe talking about it will help. Okay, so just to put it in a kind of a flow chart, you can see here the way I have drawn here, and I've shown a very shorthand notation here, which is like a 4-valent vertex with the legs at this 4-valent vertex. So typically one could draw, are there chalks here? Where is the switch for the light here? This one?
The light on the left is the one on the left.
Okay. So typically what you could have is you could have a diagram with, you could have some things like this and so on, A tree diagram which is of this type is, the way I'm looking at it is that this vertex is a trivalent vertex. This is like a, 1, 2, 3, 4, 5-valent vertex and so on. Any knot which can be brought to this kind of a shorthand notation, the shorthand notation is that the external line which I have drawn here is to be blown up as a 4-strand. This is what we call it as a finger. So you blow it up as 4-strand, and if it is at the end, you put in this capping. If it is in the middle, this is what is like a propagator. So this I call it as fingers, and each one has to be viewed as a 4-strand braid, and you have essentially this diagram which I have drawn here is like a 3-ball with 4 S2 boundaries at the 4-valent vertex. So this 4-valent vertex should be blown up and looked up as a 3-ball with 4 S2 boundaries.
I can't understand. Is this link or a knot or what is it?
It can be a link or it can be a knot, but any knot or a link, if I can draw it like this, then I call it as a arborescent knot. Or a more general one is, if I can put it in this, then I call it as an arborescent.
These are the vertices.
That's right.
This is
Yes.
the 4-valent vertex.
It could be a 3-valent, it could be a 4-valent. For this example, I've taken a 4-valent vertex alone with no propagators. But in principle, I could have...
How would the propagator look in your picture?
Yeah, here there is no propagator, but I could have propagators going on like, So let me try and draw some...
Probably means just the lines continue.
Yeah, so let me just try to draw a couple of diagrams for you. So you can put some n number of crossings here, and you could have a diagram like this for each of these fingers. Some m number of crossings here for each of these fingers. Okay, and then what you could have is you could have a propagator here with complicated and then you could have a piece which is a 5-valent piece. 1, 2. So you will have one boundary for this, one boundary for that, one boundary for this, and this one is there. So you will have one more. So this is the way the propagation will happen, and you will have a and here again you can have a finger like this. And so on. So whenever it is the end, it ends on the tree, then there you put in this kind of a finger. And even this finger, you don't need to only put crossings in the first 2 strands, it could also be a combination. So this is a kind of diagram.
In the middle you added those things. What were you doing in these crossings?
So there is a propagator here. So there is one boundary here.
Yeah, but the propagator is not just parallel lines, you just make crossings.
Which crossings? Yeah, it could have crossings also.
Propagator is what? Is there no universal
It's
definition?
connecting a 4-valent vertex to a 5-valent vertex, 6-valent vertex, and so on. It could connect.
Is there a canonical one, or you just choose all possible ones?
You can choose all possible ones.
So just drawing that diagram does not give you a unique link.
No, it doesn't give a unique link, but this is one possible way. If you can draw it in one possible way, this diagram, then you call it as an arborescent knot.
Okay.
Interestingly, I used to think that every knot can be drawn this way.
Right.
There are some knots which cannot be drawn. So 818, for example, I struggled quite a bit. At least 7 years ago, I thinking that it should be drawn. I should be able to draw it this way, but it's not possible. So those are the ones which are the non-arborescents. Okay, so it's just to give you.
Why 4? Sorry.
No, I've just given an example here.
Yeah, but why 4 strands?
Okay, so good point. So the thing is, in conformal field theory,
Just 4 fingers.
now here I put a 4 finger.
I have 8. Well, 2 hands you have 8. Yes.
Now here
She has 4 strands, 4 fingers.
No. Here I put an example which accidentally coincided with 4 strands and 4 fingers. But arborescent knots are ones where you take the boundaries. So if I start putting a boundary here on a 3 ball, you will see it like a 4 punctured S2 boundary, and that is more tractable. In the context of conformal field theory, I will put primary fields of the conformal field theory, which is a 4-point conformal block, which is much more tractable, computationally much more efficient. This is what we have seen 20 years ago, but we did not realize only this kind of diagrams are applicable to only some subset of knots, not for all knots.
But I mean, if you had, let's say, propagators and fingers with 5 strands.
Yeah, then they get onto this. They don't belong to this.
Then you could draw them like this?
No, they don't. The arborescent knots are drawn with each of these fingers having only 4 strands. That's it.
That's the definition of
That's the arborescent knots. Yeah. That's the way Conway has defined. and it was also in a Russian paper which we didn't understand, and we were struggling for 818 to draw it like this, because computationally we always knew from conformal field theory 4 punctured were easier to compute, and we were not able to draw it. And that's the time we got to know that there is something called as a non-arborescent which cannot be put in a tree diagram like this. Okay, so this one is without a propagator I've shown. I've explicitly redrawn it here. If you see it here, this is like a 1, 2, 3, 4 S2 boundaries of a 3 ball. Each one has 4 punctures, and then I cap it by a finger, which could have braiding in the middle strand in this particular example, but it could have braiding in the side strands also. Okay, so this is a very nice shorthand way of writing this diagram by putting a bar if you have anti-parallel crossings. Anti-parallel in the sense that the relative orientation between these 2 strands are anti-parallel. We put a bar and we take it to be right-handed crossings. If you have left-handed, you will put a -3 bar. Okay, and so on. So it's a very neat way of, instead of drawing the knot explicitly, if you knew what is the arborescent structure for it, we could give a tree-like diagram.
What does 3 mean?
Huh?
Why is it 3 and not 17? I don't know what 3 means.
This 3?
Yeah.
This 3 is the number of crossings here. 1, 2, 3 I put. But you can put 17, 20.
Okay.
So then you will put it as 17, and the bar means that the relative orientation between the strands is anti-parallel.
Right.
Okay. If you don't put a bar, then the relative orientation is parallel. If you put a minus sign, then it is left-handed crossing and -3 bar. So it's a very nice shorthand way of writing the arborescent knots in a very compact way.
But you're not notating the in the case where you have a propagator, you have no notation for the.
There also we will have a notation.
You have a notation for that.
Yeah. So we will have a notation. I'll go one by one.
Okay.
So I just thought I'll give a flavor of
Sure.
that 818, for example, is a closure of a 3-strand braid, and even the simplest knot I cannot put it in this diagram or that diagram.
And even in this case, so you are braiding just the middle 2 strands, right? So you're not braiding.
Not necessary. You can do other cases also. I've just put a simplest case because this is the famous pretzel example, and you can extend this by more fingers and put an invariant vertex, and you can see that, if you exchange one finger with the other finger, it is like doing a mutation. Some of these things are very nice in this diagram. So these are the famous pretzel knots and links where it has only the middle strand crossing, but in general you can have other things. Then I will put a notation that the first 2 strands, comma, second and the third and
So
fourth,
the element
and
of the
I'll
braid
put it
will-
in order also. Yeah.
So the fact that 818 has no such presentation is a theorem?
I don't know whether it's a theorem or a proof, but mathematicians have shown that it belongs to, not to the arborescent is like a tree, and you cannot draw like a tree-like diagram.
Okay.
I don't know whether it's been proven very rigorously, but I'm not able to understand that. Yeah. Only thing I can say is that we struggled for this and we couldn't draw it like this because we wanted diagrams of this type where we knew how to do the computation from conformal. Okay, so essentially, as I mentioned, the building requirement, if I want to write the states for such fingers or propagators, I need to know some kind of a basis, and that basis is given by a conformal block. The way it should be viewed here is that you compose R1 and R2, it's a tensor product of R1 and R2, and the T belongs to R1 and R2. You would see that I have introduced one more small letter R, and this will keep track of multiplicity. Suppose some of the diagrams which you look at have multiplicity, then you need to put and keep track of those multiplicities. Okay, so this is why this has become one of the important piece which we did not know when we were doing with symmetric or antisymmetric. But if you start doing mixed representations, then you will have to worry about this multiplicity factor. And this, this was explained very nicely in Ju and Joker's paper in 2014.
Whose paper?
Ju and Joker's, yeah. multiplicity and this was done for a specific representation where he had taken this representation and he considered only knots. If you look at only knots, then you can put all the representations to be same, and only thing is, depending on the orientation, you have to remember some of them will be conjugate. If your ingoing line, suppose you have an ingoing line and you give an R, an outgoing line we need to denote it by a conjugate of that representation. And for this specific representation, which he calls it as 2, 1 diagram, this color he worked out, he looked at these bases, and you need to also find a matrix. These two are two equivalent bases, and you should be able to find a unitary matrix which relates them, and this is known in the conformal field theory language as fusion matrix or duality matrix. And interestingly, the properties of this duality matrix are exactly like the Wigner 6J. In fact, it's quantum Wigner 6J. Okay, so and this is not known. Unlike your SU2, this matrix elements are not known for SUN or SON. So formally, like figure 8, this finger, as you see, I am not only put it in middle strands, but I could also put it on this. So it's like 2 fingers, just you glue these 2 fingers and you get the knot, which is 4-1, and you can see that there is braiding involved in the middle 2 strands as well as side 2 strands, and to go from the middle 2 strands to the side 2 strands, you need to use this duality matrix. So whenever you have a braiding in the middle 2 strands, and suppose they are parallel, then you will write this in a basis which is of this type. Okay, so you will have R, let's say this is parallel, and you have a representation here which is S, and you could also have a multiplicity associated with it as R2, and you will write the braiding operator, which you have to operate twice in the middle 2 strands, and if you do this, then that will give you a lambda eigenvalue, which I will denote a plus to remember it is parallel. You can also put R, R, and this is twice on the same basis. Okay, so it is like a eigenbasis. This conformal block is an eigenbasis of braiding in the middle 2 strands. If you want to do the braiding in the side 2 strands, you have to also remember that at every boundary the ingoing arrows should balance the outgoing arrows. So you could see this, that there will be anti-parallel here, and you will have an anti-parallel crossing here. And you can also check the handedness, and similarly you can work out for this case, again there is braiding. So let me call this as a 2-3 strand, this is 1-2 strand, and here the basis has to be necessarily this. Okay, so this will be T, R1, R3, and you can take R bar. So this will keep track that S is R cross R bar, S is R cross R, and T will be R cross R bar, because they are anti-parallel, and we can write the eigenvalues . Okay, so it also switches the, when the braiding happens twice, it will bring it back to the same. If it happens once, then it will exchange the arrows. So this is the procedure to write the Braiding eigenvalues. I have not given you what these eigenvalues are, but it is known in terms of quadratic azimuths. But you should also know that these two are equivalent bases. You should be able to go from this basis to this basis by the duality matrix. Okay. So when I want to do this operation here, I could write this as B23 squared, B12 squared. This is anti-parallel. This is parallel. This has to operate on the identity state. Okay. So this is the operation which I have to do to get the state corresponding to this. And this operation, when it does it on this one to do the two crossing, I need to use this basis. So I will write the state corresponding to this, I will write it as this one to start with. Okay. And then after I do this, to operate this, I have to convert this basis into this basis. So to that I will have a lambda plus squared S R2, and then I will have a AST matrix, which is the duality matrix, and then I will do the lambda T minus squared, and then what I get is the state. Okay, so the state will turn out to be finally apart from the multiplicity index and so on. Okay. So it's a very systematic exercise. If you know the Braiding eigenvalues and the duality matrix, you can systematically write out any states for these cases. And if you do the capping, you need to remember that this capping also has a state which I have to take it as an inner product with this, and that inner product, these two should combine to give me a line which is a singlet. So I will reduce it to the t equal to 0 situation. Okay. So this is the procedure which we employ, and whenever we write the invariants, it will involve the Braiding eigenvalues and the duality matrix elements. It's as simple as this, that we could write any knot invariant, at least the arborescent knots, you could rewrite using these Braiding eigenvalues and the duality matrix. The only question is that I know the Braiding eigenvalues in the polynomial variable q and a in the context of home fly PT, but what is missing is that I still don't have a way of writing these matrix elements in terms of q and a for arbitrary representations. So that's where we lack, even though we can write formally the invariant, to write the polynomial form is still a question mark for arbitrary representations. And without this polynomial invariant, verifying lot of topological string duality conjectures and all is not possible. If you want to verify some of these conjectures, for simple knots, we still have, for simple representation, we still have the verification, but for arbitrary representation, it's still an open question. Okay, so just to give you more, this is what I tried to little bit blow up and draw it like a, a finger with k such fingers, and you can draw 3 such fingers, and as I said, you don't need to be very specifically on middle strand only, that is for the pretzel type, but you can have these things, and each of these fingers I know how to work out the states, and in principle I can write the invariant, provided I also know what is the 3 boundary state. I need to say what is the 3 boundary state, and those, before I get to it, some examples like 10152 we can draw it this way, and 1071 we can draw it this way. Incidentally, this 1071 is a chiral knot, and the chirality was not detected for a long time by Kaufman, Homefly PT, or Jones. So with just a spin 3/2 put on the knots and using this redrawing diagrams like this in SU2 Chern-Simons, we could actually distinguish or detect the chirality. So in some sense, Chern-Simons or conformal field theory approach seems to be progressively powerful, is what we could say. Okay, so as I said, you need always a state corresponding to a 3 boundary, 4 boundary, and so on. So the state can also be written with including the multiplicity. For example, for this 3 boundary, you will have boundary 1 state, boundary 2 state, boundary 3 state with some factor, and this is written as a requirement of a consistency. Suppose you cap it by putting this kind of at every stage, then you are supposed to get an unknot squared, and that condition will be taken care by putting in this coefficient. Okay, and these are just sign factors plus or minus 1, which we could call it as a, which happens because of, you know, the 3G, Wigner 3J and 6J will have phases up to a plus or minus signs. Okay. So there are some diagrams here which I showed here where you know, I have something which is horizontal braiding here. I tried to tell you how you can do it when I do the vertical braiding, but if you have horizontal braiding, then it's nicer to redraw those horizontal braiding by putting it in this, you know, putting a 3 boundary, attaching this one which has a middle, in the middle 2 strands there is a braiding in the vertical direction. This diagram is equivalent to this diagram. So essentially I am trying to say that even if we have these diagrams, we don't need to really worry. We can redraw it this way by adding an additional 3 boundary surface. And there are cases where you have a loop here, and these loops can also be redrawn with our building blocks in this way. Okay, so by now I think I've at least tried to convey the fact that if you have a diagram like this, you redraw that, and you can write the states for this, and you can compute the invariants using these building blocks. So more diagrams. This is what is the propagator for you, that you have 3 valent vertex, and in between you will have a propagator, and you could try to put in crossings on the side 2 strands, or in the middle strands you can put a dot or put in those integers, and these are all parallel integers, and you can have parallel and so on. So this is looking like a Feynman-Tilly diagram, but not with a fixed trivalent vertex, but you can have many multivalent vertex. Okay, so now comes the power of computational efficiency. Okay, so what we wanted to do was that we wanted to draw one universal tree with these parameters. We wanted to write an invariant which is possible to write it in as a functions of those parameters. The parameters are nothing but your crossing numbers. So these are like the parameters. Okay, I want to put in one tree diagram. I write an invariant and tell that these parameters, if you change like this, all the knots in the knot periodic table of Rolfsen, I can give the invariant in one shot. Okay, so it's a function of parameters. The advantage in case we manage to write it in Q-Pochamer form will be that we could also do the knot quiver correspondence very easily. You know, this is one thing which will be interesting because the cases which has been done is twist knots or torus knots, but in general for any arbitrary knot it appears like it's a very difficult task. Am I right, Piotr?
You're right.
Yeah, so I think if we could write one universal tree diagram like this, which incorporates all the knots, and suppose that universal invariant I could rewrite it in Q-Pochamer, then there is a chance of looking at the quiver knot correspondence. This is one thing which I was observing, and I thought maybe it will be something which one could attempt. But I still don't have a clue how to go about looking at the invariant and converting into the Q-Pochamer form. Okay? So couple of notations here, that this is just to keep track that if the side two strands are anti-parallel, middle two strands are parallel, you have a state which is written with FAP of X. So each one could be for a kind of a finger, and you can have a propagator, and sometimes you can have crossing between side 2, middle, and then again the side 2. So some of these finger states can be explicitly written like this finger state, which involves writing it in this fashion. We have still not managed to write parameters. So here if you see, we had to have 7 parameters. By 7 parameters, what I mean is that I will have a crossing in going from parallel to anti-parallel. So there will be 1 parameter, there will be 2 parameters here, third, and then fourth, fifth, and sixth. And this kind of writing it compactly seems to include all the knots except these things. Okay, so we have not really achieved everything, but I could say that this is like a, if not measure zero, maybe a few number of knots are missing in this universal invariant which we could write. Okay, but still we have not attempted to write it in Q-Pochhammer form. This is something which I was thinking in the workshop. Maybe it's possible to write and get to looking at the knot quiver corresponding. Okay, so these diagrams which I have drawn, as I said, there should be, if there are 2 ingoing arrows, there should be 2 outgoing arrows. There are 2 possibilities. You can have the side 2 strands being parallel or side 2 strands being anti-parallel. So these are the cases which will allow, at least for the knots, if you want to look at knots, the representations will be same. Some could be conjugate, 2 of them have to be conjugate. The order of 2 of them being conjugate are 2 different types of duality matrix, because you can see here S is an element of R bar cross R, S1 is an element, this one R cross R bar is S, and here it is R cross R. So this depends on parallel tensor product, this S depends on anti-parallel tensor. Okay, so these are the only 2 types which we have to deal with, and we have to write those invariants using these 2 types. But if we do non-arborescent, as we have seen, you have more than 4 punctures. This is not really useful. In only the 4 punctures, you have representations which are put, which is the R representation. But in the non-arborescent, you will have higher dimensional conformal blocks. You don't just have 4 punctured, you can have 5, 6, and so on. In fact, it should be even number, since anything ingoing should come outgoing. So for them, you cannot just work with these 2. There are more duality matrix which is required. So what is the status which we have is that Kirlo-Reshtigan gave a very nice closed form expression, which is very useful. So in the sense that whether it's arborescent or non-arborescent, I don't need to worry about it. Not only those 2 types, it is for any type with different representation. So you could write the colored Jones polynomial in polynomial form SU2. Okay. Yeah. Okay. Yeah. So colored Jones polynomial for SU2. But of course, for all our large n dualities which we want to do, this SU2 is not really an useful information. You need to go beyond SU2. And interestingly, in 2013 with Satoshi and Zodin, we found a nice Q-Pochhammer way of writing the Swiss knot invariants, SUN. In fact, we even wrote the super polynomials. And looking at this in 2 ways, in the tree diagram way as well as from the explicit result, we could conjecture a form for the duality matrix. Okay. So what we could conjecture is that for symmetric and antisymmetric representation of SUN, so in fact we did it for symmetric, and we argued by the yesterday's mirror duality, we don't know why it works, Q to Q inverse, we could get the duality matrix for antisymmetric representation. So recently in 2014, Ju and Jokers came up and gave us a 2, 1 duality matrix for both the types. But this representation is really, it involves multiplicity, and it's very tedious using primitive conformal blocks and working out systematically all those pentagon identities. They beautifully got all the elements. Okay, so the matrix turns out to be like a 10 cross 10 matrix, and I still feel their methodology is very straightforward. Even to go beyond 2,1 to 3,1, I'm still not sure how difficult is the computation. Okay, so it is tedious, and it is very, it's not very clear. These also would have a multiplicity too, but there should be a way of trying to get some info from here and write a Kirillov-Reshtikin kind of formula even for these representations, which should incorporate multiplicity. Okay, so this is something which is still an open question. The non-multiplicity, it's a multiplicity free. If you take tensor product of vertical two box or these rectangular boxes, tensor products don't have multiplicity. Even this case, from various other methods of non-arborescent invariants, these duality matrices are known for these representations up to 6 boxes. Okay, 6 boxes in the first row and 6 boxes in the second row. So challenging problem, it's still an open problem to write a Kirillov-Reshtikin type for the SUN. So this is something which needs completely, a radical thought, and writing this will also help various other quantum group people, the quantum Wigner 6J symbol, which I think is probably like the way we did here. Maybe there is a way from knot theory to write a closed form Kirillov-Reshtikin type of formula. Okay, so this is where I think we still are, working ahead on these aspects. A couple of things, as I said, the chirality. It turned out that this conformal field theoretic approach was appearing to be powerful. Other class of two tangles where you can do a 180-degree rotation about any of these axes because it's projected onto the plane. One of the rotation is not independent. So you can try to see what happens within the conformal field theory approach. What is seen is that if you put symmetric representation, it's not new. Morton has given a proof that symmetric colors will not detect mutation, or equivalently, whenever there is no multiplicity index, it is appearing to be an identity operation. So this operation is a non-trivial operation. If you have a non-trivial room here in a two-tangle, this is a non-trivial operation, but unfortunately, none of the symmetric representations, also antisymmetric representation, I think for that matter even rectangular box representations, they will be able to detect because there is no multiplicity index. So the multiplicity index seems to play a very crucial role. So we need to go beyond symmetric, maybe I should say multiplicity free. You have to have multiplicity dependent representation is more appropriate to say here. So this is where Yuan-Joker's result on 2,1 was very useful because that has multiplicity dependent piece, and we tried to use our technology of writing the explicit polynomial form for the famous mutant knots, which of course from Morton's work for SUN n equal to 4, he had tried to show that one difference between the mutant knots is non-zero. And what we wanted to do is just do the conformal field theory way of explicitly finding out the polynomials for the examples which are mutant knots. This is the Kinoshita-Terasaka-Conway mutant pair, and check out whether they are different, and we explicitly worked out the polynomial and checked that they are indeed distinct, and we also checked that our results are consistent for n equal to 4 with Morton's difference answers and so on. Okay, so this is something which, as I want to put it here, is that if you want to detect mutation, you have to look at representations with multiplicity. If you take a tensor product of 2,1 representation, this representation occurs twice, and this is the small little r index which I was using in the presentation. Yeah, and then we tried to give a braidward way of looking at the mutation formally and how those states are dependent on plus or minus signs, and they are no longer an identity state if you have multiplicity. If you don't have multiplicity, this will only be a +1, so you will get back the state to be like the original state. Okay, so it's like a formal way of showing the proof that it is not an identity operation whenever you have a multiplicity index. Yeah, so this is what we used, and we tried to find the difference and formally compactly put in and get that it is non-zero for the Kinoshita-Conway, and that mutant pair we showed that the difference is non-zero. But interestingly, the first diagram which I showed you, which was this pretzel fingers, pretzel type, you could exchange one finger with the other finger. That is also a mutant operation. And if all the crossings which you look at are anti-parallel, this coefficient turns out to be 0. Okay? So looks like a multiplicity 2, which gives you only up to a plus or minus sign, is still not enough. These mutants are still awaiting more results, and that requires us for the duality matrix for other mixed representations where the tensor product may have higher multiplicity. Okay, so this is something which is still an open question, and this also was mentioned in Morton's paper that you need a 4,2 at least, which will have more than 2 multiplicity to see the difference between such anti-parallel pretzel mutants. Okay, so this is just to show that we worked out these invariants explicitly, redrawing the 2 tangle in our language of, putting the fingers with these crossings, using our building blocks and working it out and deriving. Because we know these coefficients, we could write the polynomial form explicitly. Okay, so this is the status on arborescent knots, and any arborescent knot if you give me, I could work out the symmetric colors. Okay, any symmetric color, the polynomial form. Similarly, antisymmetric color by using this duality, mirror symmetry duality, Q going to Q inverse.
Total antisymmetry.
Huh?
You mean the total antisymmetry?
Yeah, both and totally antisymmetric. But mixed symmetry is still an open question. 2,1, of course, we can do it. But if you want to do other cases, we still don't have the duality matrix elements.
Is
Yeah.
that related to the talk that Sergey gave yesterday about this inversion?
I don't think so. That mirror symmetry mentioned in the morning yesterday was much simpler than.
No, okay. Okay, so that's the sum total of what is happening in the arborescent case. Non-arborescent are, there's a very different kind of methods for handling non-arborescent. As I said, it will involve closure of 4 or 3 or 4 strand braids or even more. And in fact, those kinds of ways you can also draw the tree diagram. It is not difficult. If we understand this non-arborescent, we will also understand arborescent, but this is really computationally tedious. I'll tell you what all has been happening so far. Maybe battery is not there. So it is tedious. So some of the recent works which we have done, where we tried to show some interesting results, are even for a 4-strand braid closure, we really struggled to work out the 2-colored home fly PT. Okay, it was not that easy. So even to do an R-colored for knots from 4-strand braids is still a challenging question. Okay, so there are many knots which are not in the arborescent class, even within the 10 crossing or up to 12 crossing. If you want to update those polynomial form, we are still struggling for an R-colored invariant. other interesting thing which we saw is that any knot or link, if it is obtained from a closure of a 3-strand braid, okay, it could be a knot or a link. If you have symmetric representations on them, this is for 3-strand. That was for 4-strand. 4-strand is still at this level. But for 3 strands, we have a nice way of proving that SUN duality matrix elements of this type can be mapped to the SL2, the Skirlo-Reshtikin type of duality matrix. This is something which we have given recently the proof in this 1805 paper. And this is useful for closure of 3-strand braid. This includes 818 and so on. But it's still very restrictive. We have not gone to arbitrary n-strand braid. Okay. So this is one thing which I think, of course, this method helps us to do for different symmetric colors, only symmetric colors. And the procedure is very, very, straightforward. Like we can write this. This is the work of Mironov. I think Mironov will be coming this weekend. So this is this work where you give this braid sequence integers for a 3-strand braid as A1, B1, A2, B2, and then you have a systematic way of writing the colored home fly invariant in terms of this R matrices, and finding those R matrices. If you had a 3-strand braid, tensor product of fundamental representations can give you 3 box, 2, 1 and 1, 1, 1. You can rewrite them in terms of quantum dimensions of these 3 representations. So I have given you for the fundamental. A similar procedure you can do for 2 box, 3 box and so on. Okay. So essentially, just like the duality matrix we had there is this UQ which you need to do whenever you want to do the braiding in the 2nd and the 3rd strand, and this is given by the UQ. Unlike the earlier case where I had the 4 representations to be same or conjugate, here you will have some representations which are Q. That is what happened when I showed you in the, the 3 representations are same, but this one could be an arbitrary Q. Okay, so you can we could try and figure out this and do this, but for m equal to 4 or more, it involves new unitary matrices, and there is an additional different method using coproduct of representation. This is also very systematic but very tedious. This is where we tried to do it for symmetric rank 2 to do the 4-strand braid. Okay. So then we got some 4 strands of 2 colored. So you will have 2 cross 2 cross 2 cross 2, and the U matrix relates the first 3 strands, and the V matrix is required to relate this way. So you can see that it becomes, as you increase the number of strands, this picture is going to become more and more tedious. So this is the status in which we have still no handle on arborescent knots, which are knots or links which are obtained from closure of 4 or more strand braids. Okay. So this is another approach of trying to formally write the braiding relations, Young mixture operators. So we had some insight from this approach, and this is where we could try to formally write for the 4-strand case with the 2 colored and validate that 2 different approaches gave the same answer. So this is the latest data that, up to 10 crossings we have calculated representation, the 2 box representation. And then we try to combine and mix and match some of these approaches where we know how to do tangles, fingers, and use it like a 3-strand kind of approach. Okay, so the list of non-arborescent knots which can fit into these kinds of kind of a hybrid approach I have listed here, and this approach helps us to find polynomials for other symmetric representations. So in that sense, we are trying to mix and match various methods, attempting to get the polynomial form invariants. Okay, so I've given some steps here, but we can discuss later. So I just want to give you the status here. R-colored home fly, at least I've conveyed to you that R-colored, any symmetric color home fly PT for arborescent knots are computable. Okay, the correct explicit polynomial form. Colored home fly PT of knots obtained from 3-strand braids for mixed representation up to 4 boxes. This also we could do it. 2-colored home fly PT of all non-arborescent from 4-strand braids recently achieved. R-colored home fly PT of non-arborescent knot, though method is straightforward, the computation is really tedious unless we can put it in the hybrid approach. Okay, so not arbitrary non-arborescent knots, we are not able to achieve this. So, and from time to time we are updating in our website, and this includes integrality. Once we have these polynomials, we also automatically go and check up the integrality conjectures within topological strings. And some of these open problems I already mentioned during the talk. One is this RR colored home fly PT. This is also multiplicity free. Whether we could get the form of the duality matrix. So we could add some more invariants for general RR colored if this could be achieved. And with several methods of tackling polynomial form of invariants, we hope to achieve a Kirillov-Reshtikin type closed form for SUN quantum Wigner 6J for not only symmetric and antisymmetric, which we know, but mixed representations with and without multiplicity, rectangular boxes without, it has no multiplicity. So all those cases we should be able to try and get some handle. Interestingly, these knot invariants are not only worked out from conformal field theory approach, there is also the statistical mechanical model way of looking at vertex. They are called vertex models. There's a way of working this out, and we also see some connection between the vertex model approach and the conformal field theory approach. And presently we have been doing some work with Ramesh Kaul and my student on trying to get some handle on, maybe there is a way of also inferring the Wigner's 3J is what we guess. Extensions of our method to link and multicolor link invariants. So this is also something which I find it exciting. Using these link invariants, the entanglement between toral boundaries, entanglement between different S2 boundaries can all be tried to look at. And there's something called as an entanglement negativity for hyperbolic knots, which is non-zero. So maybe there is a Keshev's way of, Renat is here probably, Keshev's way of looking at the way we looked at the large, the way we tried to relate volume conjecture to the large and color of Jones, you could probably have some relation to this. This is something which we are exploring, but we have not really made any progress on this. And the last, which I've already mentioned, is that using our universal invariant, which almost governs all the arborescent knots up to 10 crossings, not everything. Maybe if we rewrite it in a Cuyp-Pochhammer form, then we could attempt the knot-quiver correspondence. Okay, thank you.
So you do that for SUN invariants and KITP. Do you have also this SO?
Yes. So SON also we have some results, but it is not as, at least for the adjoint representation, there is a universal method of looking at SON, all the other groups also, but not for arbitrary representation of SON. We don't have a clarity. But using that, we have verified also the unoriented topological string amplitude integrality conjectures for some representations. But we have not managed to do it like arbitrary representations like here.
So is there a hope to use colored complete to decide if a knot is arborescent or not?
I don't know. I don't think so. I don't think so. So you're saying if you look at the polynomial, I should be able to say whether it is arborescent or... I don't
Not
think...
just computation, but the actual polynomial.
I don't think so. I don't have a... I don't think so.
So do you expect that there is any invariant which would tell you you compute something from just some representation, not when you get the answer if it is arborescent or not. Such a thing exists.
So actually, I don't know. I think color conflict separates knots and distinguishes all knots. I don't have any counterexamples to that.
Color conflict?
Color conflict.
No.
What not?
Color conflict, yes.
No, but not for the symmetric, the pretzel, anti-parallel
No,
mutants.
I mean all representations.
All representations.
So even without the refinement?
Yes, no,
Really?
that's what I think. But
There's no counterexample?
there is no counterexample.
Really?
Only
No, we have not verified. No, we have not verified even for the anti-parallel pretzel with mixed representation. Has it been done? I don't think so.
There's
He's
no
saying
counterexample.
he doesn't know any counterexample.
I'm giving
I
a
don't know
counter.
a counterexample.
That's very far from knowing that it's
Yeah.
true. But
In fact, the only system.
sorry.
It's not very far. He knows a lot about this.
No, but I mean, if you assume, I mean, even in fact, I also don't know a counterexample to a simpler one. So, colored Jones
No.
probably distinguishes knots up to mutation.
Well, okay. So that's
There are no counterexample to that.
So if that's the case, if you really believe the color conflict distinguishes all knots, why are we wasting time with the refinement?
Well,
You're not wasting your
No, but why are you saying there is no counterexample? Because I thought that we've still not found the anti-parallel pretzels which are mutants which are distinguished by the colored home fly. We guess that 4,2 will do it, but I still don't have a handle on it.
So you don't have a counterexample yet.
Sergey, you have
might
an
one
argument
soon.
this cannot be true, right? The fact that the color cannot be the whole of the environment. No? I remember when we were discussing in the context of A polynomials and all that, that you said there are counterexamples. Am I misremembering it?
I'm not sure.
No, but is it all colors is the question. All colors we still are hampered by computing the polynomial.
Yeah, all colors is infinite set, so it's hard to.
no, but
Unless we can formally show some proof like it's an identity operation you cannot see.
well, all colors is infinite. However, if you fix a number of rows, because of Q holonomicity, it's a finite amount of information. In other words, colored only with, let's say, up to 3 rows, and if they are equal for finitely many partitions, they're equal for all of those partitions. So Q holonomicity implies finiteness, but only for a fixed number of rows. If that super holonomicity were true for arbitrary number of rows, then you have a finite state.
You know this is Q holonomic for more rows than one?
Yes, we proved that with.
I thought this is just for symmetry.
No.
Just for n.
Arbitrary number, but fixed.
But rectangular or mixed also.
Either.
But in some sense, maybe one comment I should make is that the goal is not really to classify knots. That's not an interesting problem.
Well, it is to mathematicians.
Well, the goal is to, I mean, for example, refinement and then categorification is to realize three-dimensional invariants so that they're not numerical, that we get a shadow of some four-dimensional TQFT and therefore make a step toward 4D point correct conjecture compared to classifying knots. That's infinitely more interesting. So that's really why we're doing it. And that's the truth.
So we know that, well, on the level of perturbation theory, I mean, if you do perturbation theory in the trivial flat connection, so we are talking Vassiliev invariants, we know that there are exotic Vassiliev invariants that do not come from SUN. or SON, or all simply algebras. They exist in degree 12 or more. But these quantum knot invariants, which are power series of Vassiliev invariants, are not power series of random Vassiliev invariants. They have certain structure. For example, they satisfy Q difference equations, and therefore they may classify knots, even though there are exotic Feynman diagrams that don't come from a knot invariant. But maybe some coefficient, some carefully selected coefficient of color-Homfley, and its vanishing or non-vanishing, could tell you if a knot is arborescent or not. I mean, it's not impossible.
But how they distinguish arborescent or non-arborescent nowadays?
Nowadays?
How it is decided?
Hyperbolic geometry. Actually, Snappy distinguishes all hyperbolic knots, period.
But how does hyperbolicity
Comes into this picture, I still don't know.
It's a different method for classifying knots.
Yeah, but
Using
so
hyperbolic
how does Snappy do it? Or hyperbolic?
You might have to ask Jeff how this.
I have to think more about this.
Yeah, like this arborescent, non-arborescent is different. It's not hyperbolic or not hyperbolic.
No.
Yeah, it's not related.
So you mean to say that classification is already achieved by?
By Snappy, yes.
No, by colored Homfly.
That's his guess.
That's just my guess. I also don't know a counterexample to actually color conflict with at most 2 rows.
Well, we had a heuristic argument, which is why I was asking Sergei, that the refinement may carry no more information than Humphrey, but our argument was heuristic. And I thought that Sergei had a counterexample, which is why I was trying to remember what it was, because we had an argument against it like that. But then we can discuss that. Because the idea was that in this apolynomial kind of AJ conjecture and all that, you could realize that it's a concept of Calabi-Yau as a brane, Lagrangian brane of some kind, and topological string, once you set it up that way, the geometry is completely fixed, so there's no more information than that geometry in the refinement or non-refinement. It's the same answer, there's nothing more information. So that was a bit surprising that there was some distinction, I thought. Maybe I misremember.
Well, maybe that was, now I think I remember, yeah, so that was for symmetric colors, maybe. So, yeah, so if you have, this Q difference equations that symmetric colored, all symmetric colored Homfley satisfies, they give you the geometry, but that precisely Mutants, for example, are good counterexamples to that. So Mutants may have the same symmetric Homfley, but the refinement actually now detects
So refinement improves the mutants on the symmetric one. That was the point.
Exactly. Yes, I think that's the context, and that's what we were discussing in the Nonarborescent.
I see.
And that may be true already on the level of color Jones, I suspect.
So the refined color Jones version might be enough, you might think.
I suspect. If you're only going to use symmetric representation.
What is the refinement?
Well, categorification, Poincare polynomial homology. That's what we call refinement.
I'm sorry, I missed the beginning of the talk. You spoke about classification, not classification, calculation of those invariants, and you used sort of vertex model, right?
Yeah, that's the one which I'm doing now, to do the vertex model approach of.
Then you mentioned in your talk
At the end.
Kirillov-Reshetikhin
has the
phase model.
They do that, but then they have this finally the closed form expression for the Wigner 6J symbols.
Anyway, the problem is just explicit calculation, right?
Yes.
And so why do we need so much sophistication in this? Just take our matrices, calculate them, and plug in into general theory. So what is wrong in this
What you're
approach?
saying is looks straightforward, but only when we start doing it, even the 3J symbols, there is no closed form expression for the SUN.
I think this might fall in your
Yeah, and
category
also-
of tedious computation. Straightforward but tedious.
No, but what I'm saying is that SU2, you seem to have much more handle with hypergeometric series and writing it. But for SUN, even SU3, we are still struggling. So even if we can make a progress on the SU3, it will be nice. I'm assuming or hoping that this vertex model approach, like the way Kirlo Rashtikin did, could give us some insight onto it.
So say 6J symbols, are they known for SU3?
SU3 closed form is not known. Case by case, I can sit down and work it out. Like for fundamental, I could work it out.
And these are just invariants of very specific graphs, not in graphs. Very simple, not in graphs.
Yeah.
Which of them you should just calculate? It's finite problem.
No, but there's a difference between an algorithm that terminates and a formula.
Formula, okay. It's not
That's the difference. You can do skying theory, SU3 skying theory to reduce it, and you know it reduces eventually. But
Sorry,
It's
I'm
not
not a
polynomial
specialist.
time or something.
Yeah. No formula.
no formula.
If there are no more questions, we can thank Rama.